Alright, so this is the last lecture on Hamilton-Jacobi equations. We'll move on to other lectures after this lecture. So this lecture will be proving basically the existence and uniqueness of the Hamilton-Jacobi equations and the solution given by the function given by the Hoflach's formula will show that it satisfies the Hamilton-Jacobi equations and uniqueness under certain additional assumptions. We will not be able to prove the results, so basically we give the idea about the theorem and the additional conditions about it. But before that, let me consolidate what we have done in the last 5 lectures. So we have started with the Hamilton-Jacobi equation with the Hamiltonian given by h of xu or du equal to 0 with u at x0 is equal to g of x. So this is your Hamilton-Jacobi equations, and then after this we have derived the characteristic equations. Characteristic equation is a system of Hamilton's ODE, we call it. Later we have seen that Hamilton's ODE comes from elsewhere, Hamilton's ODE. So this is a system 2n equations. Okay, you have defined the characters. You can write down the characteristic equation. After that we have derived what is called the Hoflach's formula. Hoflach's formula corresponding to a calculus of variation problem, and where you want to minimize over trajectories, and Hoflach's formula gives you that minimization can be converted into a minimization of the Euclidean space, and hence you can get an explicit formula for the Hoflach. After the Hoflach's formula, of course we left it Hamilton-Jacobi equations at that stage. After that we have studied general calculus of variation problem, and then we also derived what is called the Euler-Lagrange equations. Euler-Lagrange equations. That's what we have seen that. So the optimal solution satisfies a second order ODE system. And then we have seen many examples of a Lagrangian. The minimizing function under the integral sign is called Lagrangian. We have seen examples of Lagrangian L, and one of them is our classical mechanics L. So this is a theory which is bigger than that classical mechanics. Lagrangian L, we have seen Brachistochrone problem, catenary problems, and all that. After that we have introduced what is called the Hamiltonian, and you see that there is a solvability issue, a Hamiltonian solvability issue. When in the classical mechanics this solvability issue does not arise because it automatically satisfies the solvability. But in general Lagrangian, the solvability may not be there, so you have to make it as an assumption. And after that we introduced what is called the Legendre transformation. Legendre transformation because there is a connection between L and H. L is the Lagrangian and H is the Hamiltonian. So in classical mechanics you can go from one to another, Lagrangian formalism to Hamiltonian formalism. Hamiltonian formalism is a system of 2n ODEs. Lagrangian is a second order system of n ODEs. Okay, and in classical mechanics Lagrangian describes the position and velocity. Hamiltonian, it is position and momentum. So we keep on using these things. And what in general theories, under the assumption of solvability, we have seen a connection between that. We introduced a Legendre transformation, what is called L star. You will see that Legendre transformation of L is nothing but the Hamiltonian, and Hamiltonian is H star is also. Of course, you make assumptions on L, Lagrangian L, which is continuous, cohesive, and convexity. So we are in the convex situation, and H also satisfies the same property. So it's a duality between the so it's a the two problems are dual problems basically. This is what we have done here. Now what we are going to see is that the U given by the Hoflach's formula satisfies the actual Hamilton-Jacobi equations, where H is given by the dual of L. So the U is defined via L, and then you define H thing, and we can do the other way. Given H, you can define. So if you give a Hamilton-Jacobi equation is given and satisfies the cohesivity and the convexity continuous condition, then you can define L, and accordingly you have the minimization problem. One way to other, you can go from thing under the solvability assumption. So now as we are, it's a little more technical. Let me give you a printed material here. So what we are stating, which we will not give you the entire proof, because entire proofs may take, each proof may take half an hour, and we don't have that kind of time. And you may have, those who are interested should go through the proof, and that's very important to learn mathematics. So what will the U provided by the Hoflach's formula? So you start with a L. So you say, so given L, this gives you, under the assumptions, gives you L star, which is H. That's your Hamiltonian. This is Hamiltonian. And using that, you define U via Hoflach's formula. And then you also prove that it is Lipschitz. Okay, and Lipschitz by the Rademacher theorem, once U is Lipschitz, it is differentiable almost everywhere. So that is what you are exactly assuming. So assume that L satisfies the assumption, and UG as defined earlier, where U is the Hoflach's formula minimized problem, which is also satisfies the Hoflach's formula. And G is also Lipschitz continuity. You can replace by a different condition. Then U is differentiable almost everywhere. This comes because whenever U is defined by the Hoflach's formula, then it is Lipschitz, and Rademacher theorem tells you that it is differentiable almost everywhere. So whenever U is differentiable, all that differentiable point, U satisfies this equation. And U equal to G we already proved. In a couple of classes back, we proved that U satisfies G on Rn. Okay, that means U is equal to Ux0 is equal to Gx. That's what the meaning of it. So whenever U is differentiable, this equation ut equal to h of du is satisfied. And it is almost everywhere because U is almost everywhere differentiable. So that's what so basically you try to compute your derivative of U wherever it is differentiable. So that is what and then you prove these inequalities. Okay, so you apply the Hoflach's formula very cleverly, plus the functional identity. You have proved two things on U. One is the functional identity, the second one is the Lipschitzness. So you have to use, which is a dynamic programming principle. Maybe we'll comment more about using that. So you want to compute the derivative of U both with respect to x, and so you have to compute something like this. This is a term if you want to compute your thing. You apply this is a functional identity. This is nothing but your dynamic programming principle. If you look at it. Okay, you have dynamic programming principle, and then you can do this one, and this result is this is infimum. So you can choose y equal to x, and then h cancel, you will get this equation uxt. So if you by taking y, so if you take uxt by h is less than or equal to L of q. So if you take the limit with as h tends to 0, so you will get the full derivative. You see. So you have ut So as h tends to 0, you get a t because there are n variable. This is the derivative with respect to u evaluated at q. That is how you define derivative or directional derivative minus LQ. So that implies your one way of inequality whenever. So the first inequality is slightly easier. The second inequality is the same trick we have used and used earlier in the Hoflax formula and the functional identity. So similar trick you have to use it. So you have to get a reverse identity for this one. So you have to have a reverse identity for that one, and then you start with the Hoflax formula. So you can always choose an S here. So you can choose an Z here to get this formula, you see. So you can get that one, and then you do some computations. Okay, so you have to apply this one, apply Hoflax formula, and you see this is infimum. So you can always bound by thing, but here it is a minimum. So minus sign is there with infimum. So you have to have this exact point at this thing, because it's an infimum. You cannot bound immediately by this one. So you need this exact point. And then this is the infimum. Because of the minus sign, you can bound by this thing. And then you choose very cleverly this R, S, etc. And then do some analysis. So that is what is prescribed here. So your minimum knowledge is enough. You don't need very modern mathematics to do that. So you do the computation. So apply functional identity, clever choice of the varying, because you have infimum. So you have to choose the correct values there, and the Hoflax formula. If you do all this, you get your final. So you get your final equation. And that shows that the Hoflax formula given by thing. Now there is some serious issues to tell. You already seen in the beginning. So you already obtained a solution for your Hamilton-Jacobi equations. That is you given by the Hoflax form. So if you start with the Hamilton-Jacobi equation corresponding to H, you can define L, and you can define using L. You can have the minimization problem. Corresponding to minimization problem, you can write down your Hoflax formula, and that Hoflax formula will give you the solution to Hamilton-Jacobi equations. But then that solution is in the sense of Lipschitz condition. So it is natural that to define a generalized solution as a Lipschitz continuous function satisfying the initial condition and satisfying the Hamilton-Jacobi equation almost everywhere. So you can always define a weaker sense of the solution. A Lipschitz function is said to be a solution of your PDE, and since it's Lipschitz, its derivative exists almost everywhere, and then it satisfies the equation wherever the derivative exists. But then you have seen in the beginning, if you have Lipschitz continuous functions, these solutions may not be unique. So in this generalized sense, you may get solution, but then you may also get unwanted solution. You see, so but then naturally you expect your Hoflax formula coming from physical thing. So the solution provided by your Hoflax formula should turn out to be the correct solution. But then this generalized concept of solutions will produce spurious solutions or unwanted solutions which you may not require. So how do you remove all these conditions? So you have to look for special properties of the solution given by the Hoflax formula, and that is what, and this turned out to be what is called a semiconcavity. So okay, so I will introduce what is semiconcavity here. Any function f that need not be convex is said to be semi-concave. You see, this is concave. Look at here, this function, this for C positive, this is convex. But then if you add this minus sign, this is concave. So with your function, you are adding a quadratic concave function to make your f is concave. That may not be the kind of fully motivating thing. What is more motivating is this proposition. Okay, the proposition tells you that if starting with a continuous function, the semiconcavity is equivalent to this estimate. This is what is called a one-sided regularity estimate. One-sided second derivative. If you look at it here, this term, this is something is a kind of, if everything is nice, this is a kind of approximation with 2 by 2h or whatever it is an approximation to your second derivative. So it's a kind of approximation. So you don't have first derivative or second derivative, you have only continuity. So you have one-sided derivative. In a smooth sense, if you know that when you expand it, you can write down that as an expansion if it is differentiable 2 times or something like that. So what you are saying is that the semiconcavity is a one-sided derivative estimate. So you don't have the full regularity, but you have some sort of a one-sided second order regularity estimate. Okay, so that is one side, or only one side you get that one, and your proof is given here. So the semiconcavity given as a very nice definition. If f is semiconcave, f minus c mod x square is concave. That means you are adding a concave term with a large concave term, with a quadratic but a large term. You can make it. If you can do that, that's called concave. And but you can construct that many examples. I don't want to give it a proof here, but then semiconcavity is equivalent to this estimate. So what you are going to show is that your our u given by the Hoflach's formula satisfies such an estimate, and then under that estimate you have your unique solution. And the proof is given here. If you want, some of the proofs I have presented here, but I don't want to even read that. You can actually go through it, and it's not very difficult. Okay, so that proof is not there, but there are some more difficult proof. Some of them presented here, some of them you can refer the book. There is also another notion of convexity, because you need to assume conditions on G. If you don't have G, so you get concavity for U, you need concavity for G. Starting initial condition, which is natural, but you can also give a in terms of a uniform convexity. So the function h is called uniformly convex. H is a C2 function. Oh, that one. H is a C2 function. So you can understand it Hessian. So this is some sort of an ellipticity. Okay, kind of ellipticity. Okay, ellipticity. So uniform convexity is that ellipticity. A function h is called uniformly convex if this condition is satisfied. The d square h is nothing but your Hessian matrix. Okay, Hessian matrix satisfies this uniform ellipticity. Theta is a constant which is true for every psi in Rn. So d square h is called like semiconvex. And here is your next theorem which I want to state. If either h is semiconcave, either G is semiconcave or your h is uniformly convex. So you recall this. These are the two data given. So you have now your h of du equal to 0 and u at x0 is equal to g. So that means h, g are the given data. So you are making assumptions on the given data. Either this initial condition is semiconcave or the function involved is uniformly convex. Then the solution u dot is Hamilton-Jacobi equation. This is the Hamilton-Jacobi equation with initial data g given by the Hoflach's formula is concave. So you see now you have your Hamilton-Jacobi equation is given. With that Hamilton-Jacobi equation h, you define h gives you L, right? Because h is, you are assuming all that conditions, uniformity, continuity, cohesivity, all that. H gives you your L star. L is equal to h star. You can define that. Okay, and that gives you your u by the Hoflach's formula, which is semiconcave. That's what we, and the proof is little longer. So as I said, I don't want to read again the proof of this here. So you can go through this proof. As I said, you have to take the minimizer properly because it's given by the Hoflach's formula. Naturally, you have to take that. It's a clever way of choosing your minimizer points. Because that's the best solution for that. When you have a minimum of something, you are always looking for at what point the minimum is achieved. And that's the point you will be looking all the time. And then you have to prove this estimate. So finally what you get is that you get some sort of G is semiconcave. So first case is when assume G is semiconcave. Using the semiconcave, you prove this semiconcavity of for some G. So you are estimating this with respect to X, semiconcavity with respect to H for every T. That's what you are going to do that. So since G is semiconcave, you have this estimate. So it's just choosing your correct. So you are just computing that because it's given by the Hoflach's formula. So you are basically choosing this X star here. You see the Hoflach's formula given here. Okay, and that's all you are choosing there. Okay, and you also given a proof in the case of when H is uniformly convex. So you have a little bit you have to show that. So as this, using the uniform convexity of H, you first prove some tricky inequality. So this involves a little more work because you apply Taylor's theorem because H is a twice differentiable function. Using that you have to derive some estimates on H. After that estimates, you derive some estimates on L. You see, so with that you derive. So these are all technical, a little more technical thing. And using that technical thing, there is one more result which is highly technical. But for this, I am giving the proof here. For other thing, you will give here. So you see, you prove this. Of course, this is for each T you are proving. So you have the last inequality derived for L previously from here. So you have your, you see, inequality, which is semiconcavity. You have proved it. Yeah, so the constant of course depends on T in general. Okay, because you are proving your semiconcavity for with respect to the X variable. Okay, all right. With that, we are into a definition of the generalized solution and uniqueness. Why we need this additional condition? The generalized solution as a Lipschitz solution will not guarantee you the uniqueness. It will guarantee, it is already given the existence but doesn't give you the uniqueness. But the uniqueness proof is very, very highly non-trivial. So I don't want to even tell anything about it in this class. So those who are interested, and which you need to understand the analysis properly. It's to understand the proof of the uniqueness. But let me explain to you the main thing. So let me note the initial value problem. Let me note here. We say that a Lipschitz continuous function. So read it carefully. A Lipschitz continuous function U is a generalized solution. These are the standard conditions. Because it's a Lipschitz continuous, it is differentiable almost everywhere. So you want these two satisfy, which we have already proved. There is a uniqueness. And then generalized solution, you add this condition as well. So this satisfies the second one-sided derivative estimate. And you are given with the C positive. Okay, so if a function, Lipschitz continuous function satisfying the estimate and satisfying the initial condition and then satisfying the Hamilton-Jacobi equations in the almost everywhere sense, then it is called a generalized solution. Okay, and what the final theorem which I will state today and the final part of my talk in Hamilton-Jacobi equations, you have your existence and uniqueness, existence of a weak solution. So you have your, consider the IBP which we have described. The IBP is UT, H of, again I am repeating, so that you are equal to 0 and U at x0 is equal to gx. This is your Hamilton-Jacobi equation with H and G are given. Okay, and define whether Hamiltonian is convex and cohesive. You need that assumption. Either the initial data G is Lipschitz continuous. Assume the initial data is Lipschitz continuous, and assume that either G is semi-concave, Lipschitz continuity you are starting, or semi-concave, or H is uniformly convex. Then the function U defined by the Hoflach's formula. And what is your L? L is not given to you. As I said, H gives L. Now, H gives L as the Legendre transformation. Okay, and definition, so H implies L. And then your Hoflach's formula is this one. Is the unique generalized solution of the IVP generalized solution in this sense. This is the generalized solution in this sense. Okay. So you have your generalized solution, that one, and your Hoflach's formula given by this one is the unique solution. Okay. So I will more or less finish here, and maybe in a couple of minutes I will just remark something and okay. All right. So all right, it's not picking up. All right. So now we have a consolidated picture about it. We already told you about the consolidated picture, but then what we have proved is defined in this lecture. We have defined the weak solution, Lipschitz continuous function satisfying as a one-sided derivative estimate is the unique solution, and the U given by the Hoflach's formula is the unique solution to Hamilton-Jacobi equations. So the remarks, which some of the points which we have done, we have only studied a very particular equation ut equal to in a very special case. A general theory requires something more than that. So as you know that in 1940s, so the people have understood in the first part of the 20th century, generalized concept of weak solutions are important, and one of the breakthrough in the 1940s started from 1900 is the theory of distributions. Theory of distributions. Okay. But then this is typically a linear theory. Typically a linear theory can apply to nonlinear problems as well. Nonlinear problems. Not for a problem. But not for general nonlinear problems. Not for general nonlinear problems. That's not possible because there is no way. See, if you want it, for example, you can apply it to conservation law. You will see this in the next set of lectures, which is a set of nonlinear problems. So this has some sort of a variational structure. Variational structure. That means you need some sort of an integration by parts. Okay, but if you look at the problems here, even mod du equal to 1, and this does not have any variation structure, you cannot do any integration by parts formula. So general nonlinear problems is not easy to handle, and this happened in the 1940s. But for this, especially Hamilton-Jacobi equations from the calculus of variations, but more general Hamilton-Jacobi, Bellman equations and Hamilton-Jacobi-Isaacs equation, these are all mainly started. The theory became very, very important in the 1960s, and one of the principles was that a functional identity type inequality, what are called dynamic programming principle. Okay, and as I said, if you have smoothness, its infinitesimal version. Infinitesimal version gives you Hamilton-Jacobi equation. So especially this optimal control theory became very, very important in the 1960s. So you need to have a new type of variational, new concept of. So this distribution theory concept will not be helpful here. So you need new concept of weak solutions. We have defined in the Lipschitz thing, that's for that particular class. In general, these are all not. You need a more stable weak for solutions. Okay, new concept of solution, and that is what in the 1960s or 1980s came up what are called viscosity solutions. We will not do anything here. Viscosity solutions. You see, by Crantel, you can see there are some nice article, hard to read, Lyons, Evans, and many others. There are some good books in this direction, and some of them are referred in our textbook. You can see, and there is a note mentioned in our book on Hamilton-Jacobi equations, and some references are given. So this can be applied to general first and second order equations. General first, second order non-linear equations. Non-linear equations. Very, very general equations like f, x, t, whatever you want it, du, ut, okay, du. This is the first order equation. You can add a term if you want it here. You can add something like d square of u. So first and second order. And that's a little more classic. It's not classical, but some continuous function. How do you interpret a continuous function as a solution to such nonlinear equations? And which should be stable, small disturbance should not affect that one. So I think I will stop here. So this is only a kind of tip of an iceberg of the general theory of Hamilton-Jacobi or Hamilton-Jacobi-Bellman-Isaacs equation. Plenty of people work on this area. So this is a kind of glimpse of that, what is presented here in this small set of lectures, 6 lectures. Thank you very much.